One of the most deadly earthquakes of all time took place in Tangshan, China in 1976, with an estimated death toll of 500,000 people. It measured 8.3 on the Richter scale. Now, compare that to a more recent earthquake from this year in Ishikawa, Japan, which had approximately 300 deaths, even though it measured fairly similarly on the Richter scale, measured 7.5. Now, obviously, modern architecture in modern-day Japan will be much more earthquake-proof than in the 1970s China. However, there is a much more fundamental reason related to the power of the earthquake, why one was a lot more powerful, even though they seem to be very similar on the Richter scale. Now, the Richter scale, a lot of people will see as just a regular scale like the pH scale, where each increment just means it slightly increases by 1, like my very poorly drawn numbered line here. So the difference between 8.3 and 7.5 seems quite small. However, the Richter scale is an example of something called a logarithmic scale, where each stage or each step as you go up is a different order of magnitude. Now, what that means is that between 7 and 8, the powerfulness or the measure of power of the earthquake goes up by a factor of 10. So 7 to 8 is times by 10, 8 to 9 is times by 10. So basically between 3 steps, you can go up by a factor of 1,000 in terms of the seismograph readings of that earthquake in terms of its power. Now, if you go down from 0 to 10, you'll actually find 10 to the power 10, which is 10 billion times stronger a 10 versus a 0 on the scale, which helps explain why that one is a lot more powerful. Now, that word order of magnitude you need to know for A-level physics. It's a really important idea when we're comparing big and small numbers. So an order of magnitude, one order of magnitude is a division or multiplication by 10. Now, let's have a look at some familiar numbers and see if we can work out their order of magnitude. You have to be very familiar with standard form with this, so it always helps to have your scientific calculator handy. Now, 10 to the power 1, if you put it into your calculator, 10 times by 10 times by 1 is equal to 10, and you can see all these different numbers here: 100, 1,000, 10,000, 100,000, so on and so forth. We can represent by 10 to the power something. Now, 10 to the power 0 is 1, 10 to the power minus 1 is 0.1, minus 2, so on and so forth. You're getting smaller and smaller and smaller each time. Now, for each of these numbers, if I was to mention their order of magnitude, it would be the number that's in the index. So, for example, I would say 10 to the power 2 is 100, the order of magnitude is 2. Or 10 to the power 3, the order of magnitude is 3, which equals 1,000. So third order of magnitude would be what we use to mention those numbers. Now, this becomes useful when we're comparing numbers, and we can also, just a reminder, we can use our prefixes here with tera, giga, mega, kilo, etc., because they do help with comparisons as well. So let's have a look at this question then. So the question goes something like this. How many orders of magnitude larger is the Earth's diameter compared to the diameter of an atom? So let's look at the figures first, because I wouldn't expect you to know them off the top of your head. So the Earth has a diameter of 12,800 kilometers, and the atom has a diameter of 10 to the power minus 10 meters. So first of all, let's get the Earth's diameter into a form we can compare in terms of order of magnitude. So in meters, it's 12,800,000 meters, which, if we convert to standard form, is 10 to the power 7 meters. So that then makes it a lot easier to compare orders of magnitude, because all we've got to do is to find the difference between 7 and minus 10, or 10 to the power 7, 10 to the power minus 10. So the difference is 17. So what we'd say then is that the order of magnitude is 17. So 10 to the power 17, or 17 orders of magnitude difference between those two values. Now, in physics, you should be familiar with space and very, very small things. So in physics, we quite often deal with things that are very small and things that are very big. So orders of magnitude, why are they important? Well, they do help us to compare very, very small things to very, very big things, because quite often you'll have to use both when making calculations. Like, for example, the atom, and then looking at the scale of the solar system or the scale of the universe, big numbers and very, very small numbers. But they also help us to estimate when we are making calculations, so we can check our answers. Now, let's have a look at an example for how we'd go about doing that. So, you might have had a question before, especially at GCSE, where a question asks you to work out the mass of a person, and you might mess up your calculation, you get an answer like 2,300, etc. You know that's wrong, because you know that the rough mass of a person in kilograms is around about 50 to to 100 kg. So we can do that with even more complex calculations to check if we're on the right track, basically. So the example we're going to look at is going to be to work out the power of something. So using orders of magnitude in estimating. So we're going to estimate a couple of things. So we're going to estimate the power generated by a person where walking up some stairs. So to be able to work this out, we need to make a couple of assumptions, a couple of kind of rounding. Now we're going to talk about 4-story building, just to make the math a bit easier. So 4 stories means 4 levels. So let's have a look at an equation to use first of all. So power is rate of work done, or rate of energy transferred. So the work done as the person climbs those buildings is going to be equal to the potential energy gained divided by the time. So the gain in gravitational potential energy, m times g times change in height, and the time taken. So let's go for the time taken first of all. So to climb 4 stories of a building, are we going to be talking about kind of 10 seconds, 100 seconds, 1,000 seconds? Well, probably about 100 seconds, I'd say, a couple of minutes to kind of climb those stairs. Next, let's have a look at mass. So mass of a person, I mean, that could be lots of things, couldn't it, depending on age, gender, etc. But I'm going to go with about 100 kilograms. It's definitely not 1,000, definitely not 10. So that's 10 to the power 2. Now G rounds quite nicely to 10, so that's 10 to the power 1. And the height of the building, it's not going to be kind of 1,000 meters, it's not going to be 1 meters. It's either going to be kind of 10 or 100 we've got to choose from. And you should be able to figure out it's not going to be 100 meters, that'll be really tall, so it's going to be 10. So by doing those kind of rounding and order of magnitude estimates, we can make our calculation a little bit easier, which means it's going to round to roughly 100 watts. So when we do that calculation, if it's not close to 100 or 10 to the power 2, we know we're going a little bit wrong. So let's have a look at another one now. These are going to get a little bit trickier and kind of a little more abstract. And there are definitely different ways of doing these with different assumptions, etc. Okay, so this next one we're going to look at is estimating the volume of air in a classroom. Now, obviously, depending on your classroom, depending on the shape of it, etc. But just making some order of magnitude estimates. It's probably going to be a couple of meters tall, but let's say a meter just to keep the maths easy. About 10 meters wide, about 10 meters long, roughly, kind of 10 big paces. So volume times them all together gives us a value of roughly 100 meters cubed, or 10 to the power 2. Next, let's have a look at the number of grains of sand. Now, this is going to sound a little bit insane, but if you follow and working through, you can work out by estimating a rough value for almost anything, really, like stars in the universe, trees on Earth, number of words in a dictionary, etc. So this one's going to work out the number of grains of sand in total found on UK beaches. So again, there's going to be a few assumptions here. You might disagree with some of them, but hopefully you can follow the working. So we need to answer a couple of questions to be able to do this. Number one is how big are sand grains? Number 2, how big is a beach? And number 3, well, how many beaches are there in the UK? Now, this first assumption, possibly the most controversial, because grains of sand can be any size, and obviously it depends on the beach you go on. But we're going to, for the sake of argument here, say they're about 0.1 millimeters. We're going to say a beach, roughly speaking, about 1 kilometer wide. Talk about depth and kind of distance to the sea. Obviously, it depends if the tide's out or not, but about 100 meters to the sea. Let's say about 10 meters deep. It's deeper than a meter, probably a few meters deep. And roughly speaking, about 1,000 beaches in the UK. Again, depends on what you're defining as a beach. So let's try and to make our answer a little bit simpler, let's try and keep the idea of a sandcastle in mind, because that's a bit more kind of relatable. So this is a really bad sandcastle, which is just a cube. Obviously you wouldn't make one of these, but it helps with the maths to make the volume. So if we are going to talk about a sandcastle, that's roughly 10 centimeters tall, so that's 0.1 meters times 0.1 meters times 0.1 meters. So if we're going to talk about the volume of one sandcastle, that's going to be basically 0.001 meters cubed. Keep everything meters cubed so we can compare it later. So then let's talk about, well, how many sand grains are there going to be in a sandcastle? Because that's going to help us then figure out about the beach. So let's say in the volume of one sand grain, or volume of one sandcastle. If we cube the 0.1 millimeters from earlier in meters, so 0.0001 cubed, that equals 10 to the minus 12. Divide the volume of the sandcastle by the volume of one of those grains. We've got 10 to the minus 3 divided by 10 to the power minus 12 gives us 10 to the power 9, which about 1 billion. Sounds reasonable. I don't know, it's hard to know with these numbers, isn't it? But that's what we've got so far for the number of grains in a sandcastle. Next, let's think about, well, actually, the volume of a beach. So the volume of the beach overall is going to be those three measurements, 1,000 meters times 100 times 10, 10 to the power 6 meters cubed. The volume of the sandcastle was 10 to the power minus 3 meters. That's an order of magnitude of 9 difference. So if we multiply our answer by a factor of order of magnitude of 9, we would then have 10 to the power 18. So 10 to the power 18 sand grains in one beach. Then there's 1,000 beaches in the UK, so times it by 1,000 gives us 10 to the power 21. Like I said, there's probably lots of flaws in this, but hopefully you follow the method, and you can use that with anything to estimate. Big things or small things.